Welcome, class. My name is Dr. Scott Adamson, and today we're going to build the ability to integrate something you couldn't integrate before. This function, sine x over x, does not have an elementary antiderivative function. There is no function that you could differentiate to get sine x over x. So if you'd been struggling with this integral in the past, you may have just hit a brick wall on it. But today, we're going to build a tool that'll allow us to integrate this thing. Here's kind of a foreshadowing of where we're headed. Imagine that we could replace this function, sine x over x, with a polynomial function. And let me just remind you, a polynomial function is a function that, like a quadratic, a linear function, a cubic function, a quartic function. Imagine we could replace this sine x over x function with a polynomial function. We can integrate polynomial functions, piece of cake. So that's what we're going to build today. How do we take sine x over x and find an equivalent polynomial function for it so then we can integrate that function? Here's how it starts. The most simple, basic polynomial function that we have at our as a tool is the constant function. So imagine I told you the sine of x is approximately equal to some constant function. What would be the best constant function to represent the sine of x? Well, one more caveat here. We're going to say that this is going to be true. This sine of x function is going to be approximated by a constant function at x equals 0. Now, we don't have to do x equals 0. Just making x equals 0 makes things a little bit easier. So we're going to do that. So watch this. If x equals 0, then the sine of 0 will be that constant function. The sine of 0 is 0. And so that constant function is 0. So we're going to make a claim here that the sine of x is approximately equal to a constant function, and that function is the function 0. Now, we're going to bounce over to Desmos, and I'm going to show you that this is actually true. The sine of x can be modeled by, represented by this constant function. Let's go to Desmos and see it. So we saw that the sine of x can be approximated with the constant function f of x or y equals 0. And I know that sounds a little bit crazy, but I want to show you here on Desmos that that actually is true. So in red here you see the constant function y equals 0. And right there, and right there, and right there, and right there, the function y equals 0 and the function y equals sine of x are exactly the same. Now, clearly, y equals 0 is not the best polynomial function to model the sine of x. Let's see if we can do better. So do you believe it now? The sine of x can be approximated by the constant function y equals 0, but not well. Let's build a more complicated polynomial function that better approximates the sine of x function. So eventually we can integrate sine of x over x by approximating it to be a polynomial function. So what we have so far is c sub 0 is equal to 0. Let's now move to the next most complicated polynomial function, a linear function. Let's say that the sine of x can be approximated by a linear function. Now, again, at x equals 0 will be our chosen value of x. And so let's figure out what happens here. If x equals 0, then the sine of 0 would be equal to c sub 0 plus c sub 1 times 0. Remember, we're saying at x equals 0. So sine of 0 is 0. C1, a constant, times 0 will be 0. And so once again, we find that c sub 0 equals 0, which should not be surprising because we've already established that fact. But now let's talk about this constant c sub 1. Now, most of you are more familiar with the linear function being of the form y equals mx plus b. We're just kind of moving things around. Our plus b is the c sub 0. Our mx, our m is the c sub 1, the constant, the slope of that linear function. We're just using a different symbolism for this. So we're going to find the slope of this linear function. The slope of the linear function, the derivative of the function. That's what a derivative is the slope of that function. So let's say the slope of this sine function, and the slope of this linear function should be equal if we want to model this thing as a linear function. So the derivative, the slope of the sine of x, the derivative of sine of x is cosine of x. The derivative of this linear function c sub 0 plus c sub 1x would just be c sub 1. Again, we want to make this claim of equality around x equals 0. So cosine of 0 is equal to c sub 1. Cosine of 0 is 1. So there we go. C sub 1 equals 1. What we're claiming is the sine of x is approximately equal to c sub 0, which we now know is 0, plus c sub 1, which we now know is 1x. That is, the sine of x can be approximated by 0 plus 1x. Let's go to decimals and see how it looks. So we saw on the board that the linear function y equals 0 plus 1x could be a decent representation of y equals sine of x. Now clearly not perfect, but let's just see what it looks like. So I'm going to now enter in y equals 0 plus 1x, the linear function. And we can see that it's centered around x equals 0. Remember our decision to allow x to be 0. Centered around x equals 0, we can barely see a difference between the sine function and that linear function. At least on this interval on the input values from, like, say, negative pi over 4 to, say, pi over 4, there is barely a distinguishing characteristic between these two functions. But clearly, we can do better. So we've built a linear function to approximate this sine wave, this sine of x function, and you saw that it does a great job, linearly speaking, over a small range of input or x values. To get a better approximation, to get a better polynomial function to represent sine of x, we should continue to get more complicated in our polynomial function representation. Let's go quadratic. Now we're going to do the same kind of process here. We're going to say center this polynomial around x equals 0, and we're going to continue to build kind of one step at a time. That is, we're first going to say, let's make sure that the sine of 0 will produce the same value as the polynomial at x equals 0. So let's find out what happens in this case. Sine of 0 is 0. And again, c sub 0 plus multiply by 0, that goes away. Multiply by 0 squared, that goes away. We're left with just c0, which we've seen every time so far. This is going to be a pattern. In fact, I want you to start watching for patterns. It's going to be really important for us to recognize patterns as we continue through this process. And a pattern that we can probably confidently establish right now is that the value of c sub 0 will always come out to be 0 due to the fact that when you insert x equals 0, all the terms of our polynomial are going to get wiped out except for that c sub 0. But now, like our linear function, we also want the slope, the rate of change of our sine function and the rate of change of our polynomial function to line up at x equals 0. So we'll check the derivatives, the rates of change. The derivative of sine is cosine. The derivative of this quadratic, let's go through it term by term. The derivative of a constant, 0. The derivative of the linear term of this function would just be the c1. And the derivative of c2x squared would be 2c2x. And we again want these to match up at x equals 0. So we'll allow x to be 0 in each case. The cosine of 0 is 1. 2c2 times 0 will be 0. And so again, we'll be left with c1 equals 1. Another pattern. As we go through this process, we're always going to find out that c1 will equal 1. Well, what about c2? c sub 2 is the coefficient on that quadratic term. Now, we're going to move on to the second derivative. The rate of change of the rate of change. The concavity. We want the concavity of this quadratic function and the concavity of this sine function to be the same around x equals 0 if we're going to make a representative model, a polynomial approximation. And so we're going to go to the second derivative. The derivative of sine was cosine. The derivative of cosine is negative sine. The derivative of this quadratic gave us this linear. The derivative of this linear will be, now the derivative of a constant, 0. The derivative of this linear term will just be that coefficient 2c2. Again, we want these two second derivatives to be equal around x equals 0. So we will again allow x to be 0. Sine of 0 is 0, so we really have a negative 0, or does 0 equals 2c2? Therefore, 0 equals c2. Notice 2 times 0 is 0, so c2 is 0. Now, this is not super helpful, because what we've just found out is the sine of x can be approximated by c sub 0, which was 0, c sub 1, which was 1 times x, plus c sub 2, which is 0x squared, which of course makes 0, and so the quadratic term just does not assist us in finding a polynomial approximation for sine of x. So what we should do is keep going. Let's go cubic next. So we've seen that the quadratic term of our polynomial approximation just didn't help us with that c sub 2 coming out to be 0. So let's continue to build. Let's move on to the next most complicated polynomial function, the cubic polynomial. Notice here we're now going to claim that the sine of x can be approximated by a cubic polynomial, a constant term, a linear term, a quadratic term, and now a cubic term. Now, this process, if you can see where we're going with it, we're going to keep adding terms, keep making more complex polynomials, and so we need to leverage some patterns that we've seen in the past. A pattern that we've seen is that c sub 0 is always going to come out to be 0. And that's because if we center this polynomial at x equals 0, well, when x equals 0, all the terms other than that constant term just go away. So we know that will happen each time. C sub 1 will always turn out to be 1. Remember, to get that, we took the first derivative. And on the first derivative, this will be the constant term. And at 0, the derivative of sine was cosine. At 0 was 1. So we know that's going to happen every time. C2 is going to come out to be 0 every time. And so we got to leverage those patterns. Now, let's move on to c sub 3. C sub 3 is the coefficient on that cubic term, and we're going to follow the same patterning of building derivatives to see what those constants should be. So the first derivative gave us c sub 1, the second derivative gave us c sub 2, the third derivative will help us determine the value of c sub 3. So derivative of sine, cosine. The derivative of cosine, negative sine. The derivative of negative sine is negative cosine. So the third derivative will take us to negative cosine. Now over here, go slow. The first derivative will wipe out this constant. Now when you take the first derivative of this linear term, you just get c1. When you take the second derivative, that constant will go away. The derivative of this term, the first derivative will be 2c2x. The second derivative will just be the 2c2 constant. By the time you get to the third derivative, that term will go away. So now, we only have to focus on this, the third derivative. The first derivative, 3 out front decreased by 1, so 3c3x squared. Second derivative, the 2 comes out front. 2 times 3 is 6c3x. And then by the time you get to the third derivative, we'll be left with just 6c sub 3. Now, will you all please just maybe pause this video right now and just think through the third derivative of this term using the power rule. The 3 comes out front, then the 2 comes out front, gives us that 6c3. And by the time you get to the third derivative, it's just that constant term 6c3 is all that's left. Make sure you get that before we move on. Now, third derivative, at x equals 0. The cosine of 0 is 1, so this is a negative 1 equals 6c3. Therefore, c sub 3 is negative 1/6. So here's what we can now claim. The sine of x can be approximated by c sub 0, which we know is 0, c sub 1 times x, so 1 times x. C sub 2x squared, remember c sub 2 was 0. But now we got something useful. C sub 3 is negative 1/6. So this last term is going to be a minus 1/6 x cubed. And we're going to jump over to Desmos and show you that this cubic polynomial looks very much like the sine of x for a while. We've now built a cubic polynomial that can be used to approximate the sine of x function. That cubic polynomial had a constant of 0 plus a c1 of 1, so 1 times x, and then a 0x squared. But then we finally got something useful with the minus 1/6 x cubed. Let me add that in here. And now we see in red that that cubic polynomial resembles our sine function relatively well over a small interval of input or x values. To get even a better approximation, we need more terms to our polynomial. Let's go get some more. So you've seen now the cubic polynomial working to mimic, we could say, that sine of x function. And I hope you kind of get the gist that as we continue to build more terms to our polynomial function, we will get a better and a better approximation for this sine of x function. So we will. Seeing patterns is going to be really important, though. Here's a pattern. C sub 0 was 0, C sub 1 was not 0. C sub 2 was 0, C sub 3 was not 0. Do you see that every other term in our polynomial will have a coefficient of 0? Why? As we work through this, we're going to keep taking derivatives. The derivative of sine involves cosine, and the derivative of cosine involves sine, and the derivative of sine involves cosine. So we kind of bounce back and forth between sines and cosines. Every time we get back to sine and we center at x equals 0, the sine of 0 will be 0, thus making that constant, that c sub whatever, will be 0. So when we get to our Quartic, our fourth degree polynomial term, we will again return to a derivative involving sine. We will again return to a coefficient of 0. So coefficient of 0, coefficient of 0, coefficient of 0. We're not going to get a non-zero coefficient until we get to our odd term here, the quintic, the x to the 5th power term. So let's work on it next. Now keep in mind, we know that c sub 0 is going to be 0. We know that c sub 1 is going to be 1. We know c sub 2 is going to be 0. We know c sub 3 is going to be that 1/6 that we got before. We know c sub 4 is going to be 0. So we're now going to focus on c sub 5. Now, to get c sub 5, we're going to go to the 5th derivative. All right, here we go. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine, negative cosine. The derivative of negative cosine will take us back to sine, and then the derivative of sine will take us back to cosine. So the 5th derivative will take us back to cosine. Now, go slow. The first derivative, the constant term, will go away. First derivative of this term will be c1. By the time you get to the second derivative, that constant will go away. By the time you get to the third derivative, this will go away. The fourth derivative, this will go away. The fifth derivative, this will go away. So the only thing we really have to worry about is that 5th degree polynomial term, the c5x to the 5th. So let's think about the 5th derivative. Now again, I encourage you to pause this video and maybe think through what's going to happen when you take the 5th derivative of c sub 5x to the 5th. Power rule over and over and over again. I'm just going to say it. I hope you can follow. First derivative, 5c5x to the 4th. Then 4 times 5, 20c5x to the 3rd. 3 comes out front. And then finally that last term comes out front. So it would look something like this. The first derivative will be 5c5x to the 4th, 20c5x cubed, 60c5x squared, 120c5x, and then by the time we get to the 5th derivative, it's just going to be 120c sub 5. So the 5th derivative of sine is cosine. The 5th derivative of this polynomial term is just going to be 120c sub 5. Now we want these 5th derivatives to be equal, centered at x equals 0, Cosine of 0 is 1. To solve for c sub 5, just divide both sides by 120. So 1/120th will be c sub 5. So this polynomial now is going to be 0, 1x, 0x squared minus 1/3 x cubed, 0x to the 4th. That this 5th degree term is going to be a 1/120th x to the 5th. Now, let's go to Desmos and see if this is working. We're now going to use Desmos to build this 5th degree polynomial. I know you can't see it, but I'm typing in the 5th degree polynomial that we developed on the board, that 5th degree term being 1/120th x to the 5th. And so now we see an even better approximation. Let me just kind of back up a minute and see. There was the cubic, and then now here is the quintic, the 5th degree term. We see that that polynomial is even more mimicking our sine wave. And I hope you see that if we keep going, we will build a better and better and better polynomial function to approximate the sine of x. So here we are. We now have a 5th degree polynomial to approximate the sine function. And I want us to get to a place where we can quickly get more terms without all the details that you've been seeing before, because we see a pattern. Here's the first pattern. We don't need the 0 terms. They don't add to our polynomial function at all. So let's eliminate them. What we really have now is a 1x, a 1/6 x cubed, and a 1/120th x to the 5th. So what we notice as a pattern is only the odd powers of x survive, because the even powers have derivatives involving sine. Sine of 0 is 0. Those things go away. So let's just focus on the odd powers. For instance, the next term is going to involve x to the 7th. But what's the coefficient going to be on that x to the 7th? Do you remember when we were finding these coefficients, we needed the first, second, third, fourth, fifth derivatives. And when you take derivatives repeatedly by the power rule, like in that last case, you saw the 5, and then the 4, and then the 3, and then the 2, and then the 1. There's a mathematical name for that. When you take 5 times 4 times 3 times 2 times 1, that's called 5 factorial. And so what you'll notice here is this coefficient, this 120, is 5 times 4 times 3 times 2 times 1. It's 5 factorial. So we could replace this with 1 over 5 factorial x to the 5th. Likewise here, the 3, the cubic term, the coefficient came when we took the third derivative. The 3 out front, then the 2, then the 1. 3 times 2 times 1 is 3 factorial. And even here, it's a little simpler, but this is just a 1 factorial, just 1. So we could even say this is 1 over 1 factorial x to the 1st. So I hope you see the pattern here. We can now write terms of this polynomial all day long. We see odd denominators, factorials. We see odd powers. We see plus, minus, plus. So the next term is going to be a minus 1 over 7 factorial x to the 7th. Then the next one after that is going to be a 1 over 9 factorial x to the 9th. And then minus, plus, minus, plus. This pattern will go on forever and ever. And the more terms we have, you've been in calculus long enough now to appreciate that when we go off to infinity, good things can happen. So imagine an infinitely long polynomial with all these odd powers, with all these odd factorials, that we would have a polynomial that approximates or estimates the sine of x function perfectly. Now, what we're going to do is capture this in a shorter amount of space, because going off for infinity, if I did this plus minus thing forever and ever and ever and ever, that would be really tedious. So how can we capture this in a more simplified format? It looks like this. Notice what we're doing is we're taking terms and we're just summing them up. And in math, the symbol we use for summing up is the Greek letter sigma. So we're summing up all of these terms. Now let's just number these terms. Let's put a number to them. Use a different color here. Let's say this is the first term of the polynomial. This is the second term. This is the third term. This is the fourth term. This is the fifth term. So n will represent the number of the term, first, second, third, fourth, and fifth. So we're going to allow n to go from 1, and ideally, to get a perfect approximation, we're going to go to infinity. Now let's look at the pattern here. Notice that each one of these terms has a coefficient of 1 over something. And the something that it's over, notice when n is 1, it's a 1 factorial. 2, 3 factorial. 3, 5, 4, 7, 5, 9. What's the relationship between the number of the term n and that denominator that we see? Notice if you double n, double 3 is 6, and subtract 1. Double 4 is 8, subtract 1 is 7. Double 5 is 10, subtract 1 is 9. Double 1 is 2, subtract 1 is 1. So the denominator of all those coefficients is double the value of n and subtract 1 factorial. That coefficient is in each case being multiplied by x raised to a power. And notice the power, even on this first one, it's x to the first. The power matches up with that same value factorial, 3, 5, 7, 9. And so it's going to be raised to the power of 2n minus 1. And then we have to establish that when n is 1, we have a positive. When n is 2, minus. N is 3, plus. N is 4, minus. Plus, minus, plus, minus, plus, minus. We have to alternate those signs. So what we'll do is we'll multiply by negative 1 to a power. Watch this. If I took negative 1 to the n, when n is 1, negative 1 to the 1 would be negative 1. Multiplying all this by negative 1 would make that first term negative. That's not good. Or when n is 2, negative 1 squared is positive 1. This whole thing would be positive. That's not good. So I need to back off 1. Here's what I mean. When n is 2, 2 minus 1 is 1. Negative 1 to the 1 is negative 1. All this is negative as it should be. When n is 3, 3 minus 1 is 2. Negative 1 squared is positive 1. All of this is positive as it should be. And you can check that with all of them. So what we have built here is a formula, a nice concise way to express the sine of x as an infinite polynomial. The name for this is called an infinite Taylor series, named after the mathematician Brooke Taylor. So this is an infinite Taylor series. Prior to that, we had what we call a Taylor polynomial. The Taylor polynomial centered at x equals 0 is what we established, and from that Taylor polynomial, we were able to write the Taylor series. Now, we will use that Taylor series to go back to our original question. How do we integrate sine x over x? Wow, that was a long haul, but the point is, as we build an infinitely long Taylor polynomial and represent it as a nice, concise, relatively speaking, Taylor series, we can approximate the sine of x using a polynomial function. So what you see here is I'm going to try to build a dynamic version of what you just saw happen. And so first of all, here in red is that Taylor polynomial. I've taken out all the 0 terms because they didn't help us see anything more than we could have without it. And now let's just start adding terms. So let me just kind of go slow here. There was that linear y equals 1x, and notice it fits that sine curve well for a small interval of input or x values. Then we added that cubic term, and things got a little bit better. Then we added the 5th degree, and things got a little bit better. And then we could even add that 7th degree and see that things get even a little bit better. And as we continued to add terms, things got better and better and better. Notice now here is the infinite Taylor series. Well, not really infinite here on Desmos, but I built it so that n can go from 1, the first term, y equals 1x, to a, and then we'll allow a with this slider to go up to 50. And what I hope you'll see is, as we increase the number of terms, the polynomial better and better and better approximates this function. Here we go. Let me turn this one off. Let me turn this one on. So there's that linear polynomial, that linear function. Now watch as a increases, as we go from a linear to a cubic to a quintic to a 7th, 9th, 11th, 13th, etc., etc., etc. The more terms on the polynomial, the better the polynomial matches the sine of x. Now eventually it's going to, as all polynomials do, it's going to move away from that sine wave. But if we think about this polynomial having infinitely many terms, then we can agree that it models, it represents, it approximates the sine of x perfectly. I know this is a long process, but it was important for you to build this polynomial little by little and see how all these pieces come together to ultimately have a way to express a sine function as a polynomial function. I know this is a new way to think about it as a Taylor series, but it's important. There's just one last thing. We don't always have to start counting at 1. We don't have to say first, second, third, fourth, fifth. We could instead say 0, 1, 2, 3, and 4. Now there's not a this is right and this is wrong. It's just you can do it this way as well. And if you did, it changes our polynomial just a little bit. So notice we're still summing up, but instead of starting at n equals 1, we're starting at n equals 0. We're still going to have infinitely many terms in theory. We still have a 1 over something factorial, but now what's the factorial? The 0th term has a denominator of 1 factorial. 1 is 3, 2 is 5, 3 is 7, 4 is 9. What's the relationship now? Double n, 8, add 1. Double 3, add 1. Double 2, add 1. Double 1, add 1. Double 0 is 0, add 1. So now we're doubling the value of n and adding 1 factorial. Times x to the, notice it's the same value. The 3 factorial has a power of 3 on x, so it's to the power of 2n plus 1. And we still need to alternate those signs, plus, minus, but now the good news is this. When n is 1, if I just raise it to the n power, when n is 1, negative 1 to the 1 is negative 1, so all of this is negative as it should be. When n is 2, negative 1 squared is positive 1, so all of this is positive as it should be. Even 0, negative 1 to the 0 power is 1, so all of this is positive as it should be. So if you started counting at 0 instead of 1, this would be the Taylor series for sine of x. In the next video, we're going to use this information to actually integrate sine of x over x.